Moving on. The old school methods of calculating AC power don't rely on complex number math, but rather witchery and superstition to do so. The prime source of witchery is a concept known as power factor, sometimes abbreviated PF. Power factor is the ratio of real power P over apparent power S. PF equals P over S. Note the old school methods don't use complex numbers, and as such, note S is not considered as having a magnitude and direction anymore, but rather as a scalar quantity, something with magnitude only. To calculate apparent power magnitude using the old school method, take the effective or RMS voltage and multiply it times the effective or RMS current. S equals V times I. 2. Easy. You note that apparent power magnitude obtained using this technique is the exact same magnitude as that obtained using the complex number representation. It's just that there's no angle associated with it. But don't you dare point this out to anybody using the old school methods, because all you'll get in reply is a blank, uncomprehending stare. The old school methods don't use angles and don't use complex numbers. Given known quantities, one could easily manipulate these 2-3 variable equations to solve for the remaining unknown quantities. For example, if you knew the apparent power and power factor, you could calculate real power P in units of watts to be apparent power times power factor. That's it. You might ask yourself about these old school techniques. Where's Q? What the heck is power factor? But you'll get no help from these crude old school techniques. They're purposely designed to keep all the magic well hidden behind the curtains and let dull and apathetic drones do what they do best, namely obey orders without question. Power factor is something often directly stamped on a motor nameplate. A drone will be dispatched to take 2 measurements, a voltage reading and a current reading. Multiply the voltage times the current to get apparent power. Multiply apparent power times power factor to get real power. Record the values, move on to the next task, and repeat. Despite the crudeness of these old school techniques, you can't help but admire their efficiency. It's for this reason alone that I cannot honestly say that I'm entirely new school. On occasions when I just need a single piece of data, I'll just old school it to get what I need as quickly and painlessly as possible and move on to the next problem. If, however, I need a complete and holistic picture, I'm going to bust out the arsenal of new school techniques. By the time I'm done with it, every single aspect of AC power will be cut, sliced, diced, cubed, and packaged into clearly labeled see-through containers. Additionally, as you often see me do, by using a combination of both the old and new school techniques, you can 1. Check your work, and 2. Use the new school techniques to fill in all those gaping holes left uncovered by the old school techniques, i.e., get a couple important results quickly as possible using minimal calculation, and then take your time to reel in the rest. The choice is up to you as long as you get the right answer in the quickest amount of time every single time. Speaking of gaping holes, what the heck is power factor? If you're a dull and apathetic drone, power factor is a number stamped on the side of the motor, and you don't need to concern yourself with its origin. If, however, you are more intelligent than a goldfish, you'll realize that power factor is in effect a cheat code that extracts the real horizontal x component from the apparent power vector. As we demonstrated, real power equals apparent power magnitude times power factor. Given we previously illustrated how to convert complex numbers from polar format to rectangular format and vice versa, it should be evident that power factor is a pre-calculated stand-in for the cosine of the apparent power angle when apparent power is represented as a complex number. Power factor equals cosine theta s. While we're on the subject of angles, what is theta s? Obviously, theta s is the angle of apparent power when apparent power is represented as a complex number. It's also a couple of other things, and you can use these observations to shortcut your work or check your calculations. If everything works out right, theta s should have the same value as the angle of the impedance for the element in question, theta z. Additionally, if you've referenced current with respect to voltage as required, theta s is the inverse or negation of current's phase shift, theta I. In summary, theta s equals theta z, equals the negative phase shift of current. Again, I could go on and on about the inconvenience of the assumed sign of reactive power, but all my raging won't make a difference. This is the facts, and we are stuck with it. This being said, I kind of understand the inconvenience. Given inductors are assumed to be complex impedances defined as having positive vertical imaginary components, and capacitors are assumed to be complex impedances defined as having negative vertical imaginary components, you should ultimately get an apparent power angle, either positive or negative, that favors the impedance nature of the element in question. i.e., if you're dealing with an occasion in which current lags voltage, you're most likely dealing with an inductor, and your reactive power should be positive. Conversely, if you're dealing with an occasion in which current leads voltage, you're most likely dealing with a capacitive element, and your calculated reactive power should be negative. This is where it's helpful to think of electrical properties using different yet related domains of complex numbers. The first domain is the impedance domain, where all positive real horizontal x values represent resistive effects. All positive imaginary vertical y values represent inductive effects, and all negative imaginary vertical y values represent capacitive effects. The second domain is the voltage and current domain, where voltage is always the assumed reference, i.e. the voltage phasor points at 0 degrees right on the horizontal axis, and current is referenced from this perspective and this perspective only, i.e. current leads or lags voltage and not the other way around. Current leads voltage for capacitive elements, current lags voltage for inductive elements. The third and final domain is the complex power domain, where quite like the impedance domain, all positive real horizontal x values represent real power. All positive imaginary vertical y values represent inductive reactive power, and all negative imaginary vertical y values represent capacitive reactive power. Believe me, these three diagrams are worthy of inclusion on your cheat sheet. Ironically, despite the fact that we just introduced the AC power domain and the concepts of apparent, real, and reactive power for the first time today, the power domain is not the one that students historically struggle with, but rather the voltage and current domain, something they should have ample experience with by now. The fundamental misunderstanding students have with the voltage and current domain is that, for the purposes of AC power calculation, current must always be referenced with respect to voltage. While ordinarily this is the case, it's not always the truth, especially in larger circuit analysis scenarios where some other absolute reference might be employed. This important precondition often necessitates a student calculate the relative phase shift between voltage and current. Unfortunately, students are often in a rush and neglect to perform this most important step. Don't be that student and get a wrong answer every single time. Be that student that understands current must always be referenced with respect to voltage for the purposes of AC power calculation. In summary, absolute phase shift is of little concern, whereas relative phase shift is of prime importance for AC power calculation. As a demonstration of this simple but very important process, consider voltage expressed as a phasor equivalent as 48 volts at an angle of 25 degrees, and current expressed as a phasor equivalent as 150 milliamperes at an angle of negative 15 degrees. Despite the use of some external absolute reference, it should be obvious that there is a relative phase shift of 25 plus 15 or 40 degrees between voltage and current can be said to lag voltage by 40 degrees. Therefore, for the purposes of AC power calculation, it can be rightly said that voltage expressed as a phasor equivalent is 48 volts at an angle of 0 degrees, and current expressed as a phasor equivalent is 150 milliamperes at an angle of negative 40 degrees. Don't make relative phase shift hard. Just look at the phasor diagram. For the purposes of AC power calculation, current must be referenced with respect to voltage. I'll only say this about 1,000,000 times, and I guarantee some of you will still have issues with this. Don't let it be you. While we're on the subject of angles, let me point out that the cosine function is symmetric about the vertical y-axis, meaning the cosine of 45 degrees equals the cosine of negative 45 degrees. The cosine of 63.7 degrees equals the cosine of negative 63.7 degrees, and so on, whereas the sine function is not. Sine of 45 degrees equals negative sine of negative 45 degrees. The sine of 63.7 degrees equals negative the sine of negative 63.7 degrees, and so on. Long story short, the sine function of equal and opposite values have the same magnitude, only the polarity is different. These observations mean you can get a little sloppy with respect to real power and use whatever sine of the angle you want, positive or negative, and you'll still get a correct answer because calculating real power in terms of apparent power and vice versa makes use of the symmetric cosine relationship, P equals cosine theta s. This, however, is not true regarding reactive power, because calculating reactive power in terms of apparent power and vice versa makes use of the asymmetric sine relationship, where reactive power Q is equal to the magnitude of apparent power times the sine of the apparent power angle. Q equals S sine theta s. If you use an angle with the wrong sign, you'll get the wrong sign for reactive power. This being said, all this yammering about signs aside, just remember, for inductive occasions in which current lags voltage, they're assumed to have positive reactive power, and capacitive occasions in which current leads voltage are assumed to have negative reactive power, and you'll do just fine. The magnitude of the sine function is still the same for positive and negative angles, it's just the polarity that's swapped. Alright, I do believe we've finished at least the conceptual discussion of AC power. Let's now put all this discussion to practice with a handful of practical exercises before closing out this lecture. I'll devote another lecture entirely to more AC power examples. To keep things simple, let's assume every single scenario I'm about to present to you has the same effective value for voltage and current, only the degree by which current leads or lags voltage will differ. For this illustrated example set, voltage will always have an effective value of 120 volts, and current will always have an effective value of 0.7 amps, or 700 milliamperes. You should observe a recognizable pattern as we walk through this set. Additionally, you should anticipate our calculated results to correlate with our previous general expectations regarding how the degree of phase shift between voltage and current allots apparent power into real and reactive portions. Our first plot shows voltage and current to be perfectly in phase with one another. Our previous thought experiment led us to believe that there will be no cyclical exchange of negative and positive power. As such, reactive power Q should be equal to 0 VARs. Given none of apparent power is being directed towards a reactive interchange, we should expect all of it being directed towards real power. In summary, for occasions in which voltage and current are perfectly in phase with one another, we should expect S equal to P and Q equal to 0. Let's see if this is the case. Let's use the new school methods making use of complex numbers. The phasor representation of voltage would be 120 volts at an angle of 0, and the phasor representation of current would be 700 milliamperes at an angle of 0 degrees. Apparent power is the complex conjugate of the voltage times current. Substituting our given values, we arrive at a value of 84 volt amperes at an angle of 0 degrees. The complex conjugate of 0 degrees, by the way, is 0 degrees. Let's now resolve apparent power into real and reactive components. Real power equals the apparent power magnitude times the cosine of the apparent power angle. P equals S cosine theta s. Substituting in our given values yields real power equals 84 watts. Reactive power equals the apparent power magnitude times the sine of the apparent power angle. Q equals S sine theta s. Substituting in our given values yields a reactive power of 0 VARs. As we anticipated, for occasions in which voltage and current are perfectly in phase with one another, all of apparent power is being directed towards real power because none of it is being directed towards a reactive interchange. Let's try another illustrated example, only this time featuring an occasion in which current lags voltage by, let's say, 30 degrees. Assuming our magnitudes remain the same, the phasor representation of voltage would be 120 volts at an angle of 0 degrees, and the phasor representation of current would be 700 milliamperes at an angle of negative 30 degrees. Voltage and current are in almost every aspect exactly the same as in our previous example problem, only this time, current lags voltage by 30 degrees. Our earlier thought experiments led us to believe that given an increased phase shift between current and voltage, we should anticipate an increased cyclical exchange of negative and positive power, and as such, reactive power should increase. Given a larger portion of apparent power is being directed towards a reactive interchange, we should expect a smaller portion of it to be directed towards real power. Long story short, real power goes down and reactive power goes up. Additionally, since this is a slightly inductive scenario in which current lags voltage, we should expect our reactive power to have a positive value. Let's use the new school methods making use of complex numbers to see if this is the case. Apparent power is the complex conjugate of the voltage times the current. Substituting in our given values and performing just the multiplication, we arrive at a value of 84 at an angle of negative 30 degrees. Taking the complex conjugate of this product yields an apparent power figure of 84 volt amperes at an angle of positive 30 degrees. You'll note the apparent power magnitude is the same value we obtained earlier for the occasion in which voltage and current were in phase with each other. Only the angle of apparent power is changed. As previously, we can resolve apparent power into real and reactive components. Real power equals the apparent power magnitude times the cosine of the apparent power angle. Substituting in our given values yields a real power figure of 72.7 watts. As we anticipated, real power has gone down. Reactive power equals the apparent power magnitude times the sine of the apparent power angle. Substituting our given values yields a reactive power of positive 42 VARs. Reactive power has gone up. Additionally, note reactive power has a positive sign, indicative that the element in question is slightly inductive in nature because current is lagging voltage. As we anticipated, less apparent power is being directed towards real power because more of it is being directed towards a reactive interchange. While we're here, let's test out some of the other means one can use to calculate AC power. Ideally, we should get these same results. Let's first use Ohm's law to determine the impedance of the element in question. Impedance equals voltage over current. Substituting in our given values yields an impedance value of approximately 171.4 ohms at an angle of 30 degrees. The positive 30-degree impedance angle indicates it's slightly inductive in nature, as we'd expect. Apparent power can be calculated using the formula S equals complex conjugate of the current squared times impedance. Use of this formula requires knowledge of both current and impedance, but does not necessitate knowledge of voltage. Substituting in our given values, we again arrive at an apparent power figure of 84 volt amperes at an angle of positive 30 degrees. Apparent power can also be calculated using the formula S equals the complex conjugate of voltage squared divided by impedance. Use of this formula requires knowledge of both voltage and impedance, but does not necessitate knowledge of current. Substituting in our given values, we again arrive at an apparent power figure of 84 volt amperes at an angle of positive 30 degrees. As previously, any of these results could be resolved into the real and reactive components of 72.7 watts and positive 42 VARs. This just goes to show you that there are many, many ways to get correct results. Also note, regardless of the calculation method employed, the apparent power angle is equal to the impedance angle. Additionally, note the apparent power angle is equal in magnitude, yet have the opposite sign of current's phase shift with respect to voltage. These angle checks make handy references for the purposes of checking your work. Just for the heck of it, let's now try the old school methods. Ideally, we should get the same results. Anyone making use of the old school methods is ordinarily given a power factor figure in advance. This pre-calculated data is often written right on a motor nameplate. This being said, since the means of doing so are right in front of us, let's see if we can calculate power factor. There are several means of doing so. Power factor is the ratio of real over reactive power. Power factor is also the cosine of the apparent power angle. Additionally, since there exists a relationship between the apparent power angle, the impedance angle, and the relative phase shift angle between current with respect to voltage, one could also say that power factor is the cosine of the impedance angle, as well as the cosine of the inverse of the relative phase shift angle between current with respect to voltage. Additionally, since the cosine function is symmetric about the y-axis, power factor can also use the amount of phase shift between current and voltage without accounting for sine. Long story short, there are many ways of calculating power factor, and they all yield the same value. in this case a power factor of approximately 0.8660. If we walked up to a box that said power factor 0.8660 on it and took a voltage and current reading, we'd have the following values: 120 volts and 700 milliamperes. In this scenario, we aren't made aware of any phase shift between voltage and current. All we'd have is a power factor figure and two effective magnitudes. If we multiply voltage times current, we get apparent power. Substituting our given values yields 84 volt amperes. Note, using the old school methods, apparent power is a scalar quantity, meaning it has magnitude only and no direction. One can solve for real power as apparent power times power factor. Substituting in our given values yields 72.7 watts. That's it. The old school methods yielded the same results for apparent power and real power in short order. That might be all well and good, but where's Q? The old school methods aren't really sophisticated enough in and of themselves to concern themselves with foofy reactive magic. We, however, are not some dull and apathetic drones and are keenly aware of the behind-the-scenes relationship between apparent, real, and reactive power. Here's one such way of calculating reactive power. Given the magnitude of S equals the square root of the sum of the squares of P and Q, we should be able to algebraically solve for Q. Doing so yields Q, reactive power, equals the square root of the differences of squares S and P. Q equals square root S squared minus P squared. Substituting in our given values yields a reactive power of 42 bars, exactly as previously. Here's another means of calculating reactive power. Reactive power equals apparent power magnitude times the sine of the apparent power angle. From our previous calculation, we have the magnitude of apparent power, but using the old school methods, we're not directly aware of the angle. This being said, given we know power factor to be 0.8660, after all, it says it right on the side of the box, we should be able to determine this angle. If power factor is the cosine of the apparent power angle, we can solve for this angle by taking the inverse cosine of power factor. Substituting in our given values yields an apparent power angle of 30 degrees as previously. Substituting this angle and apparent power magnitude into the reactive power formula again yields a reactive power figure of 42 VARs. Again, don't get discouraged by the variety of techniques I'm demonstrating. Take heart that with so many techniques at your disposal, at least one of them should work. Pick up a tool and swing it wildly until you get an answer. If the handle breaks off before you get an answer, pick up another tool and keep swinging it wildly until you get an answer. Repeat, repeat, repeat. In this spirit, let's try yet another illustrated example. Here's a plot of voltage and current where current appears to lag voltage by a full 90 degrees. The phasor representation of voltage would be 120 volts at an angle of 0, and the phasor representation of current would be 700 milliamperes at an angle of negative 90 degrees. Voltage and current are in almost every aspect exactly the same as in our previous example problems, only this time current lags voltage by a full 90 degrees. Our earlier thought experiments led us to believe that given a phase shift of a full 90 degrees between current and voltage, we should anticipate a zero-centered power waveform with equal and opposite periods of positive and negative power. Given all of apparent power is now being directed towards the cyclical interchange of reactive power, we should expect none of it to be directed towards real power. Long story short, for occasions which current lags voltage by a full 90 degrees, real power is 0, and the absolute value of reactive power equals apparent power. Let's see if this is the case. Apparent power is the complex conjugate of the voltage times the current. Substituting in our given values, this yields an apparent power figure of 84 volt amperes at an angle of positive 90 degrees. Again, you'll note apparent power magnitude is the same value we obtained previously, since we're using voltage and current with the same effective values. Only the angle of apparent power has changed. As previously, we can resolve apparent power into real and reactive components. P equals S times cosine theta S. Substituting in our given values yields a real power figure of 0 watts. Given the power waveform is zero-centered, this is to be expected. Power consists solely of a cyclical interchange of positive and negative power, and the average is 0. Q equals S sine theta S. Substituting in our given values yields a reactive power figure of positive 84 VARs, meaning that all of apparent power is now being directed towards the cyclical interchange of reactive power. Additionally, note reactive power is a positive sign, indicating that the element in question is inductive in nature and current lags voltage. In summary, all apparent power is now being directed towards a reactive interchange because none of it is being directed towards real power, exactly as we anticipated. Power analysis needn't be limited to scenarios with lagging current, but can also be calculated for occasions in which current leads voltage. Note, because of predefined sign conventions, capacitive scenarios in which current leads voltage, reactive power is assumed to be negative. Here's a plot of voltage and current where current leads voltage by, let's say, 45 degrees. The phasor representation of voltage would be 120 volts, and the phasor representation of current would be 700 milliamperes at an angle of 45 degrees. Voltage and current are in almost every aspect exactly the same as in our previous example problems, only this time current leads voltage by 45 degrees. Our earlier thought experiments led us to believe that given a phase shift between voltage and current, we should anticipate a cyclical exchange of reactive power. Given a portion of apparent power is being directed towards a reactive interchange, we should expect real power to be less than apparent power. Additionally, since this is a capacitive scenario in which current leads voltage, we should expect our reactive power to have a negative value. Finally, given 45 degrees is halfway between 0 and 90 degrees, we might expect apparent power to be resolved in x and y dimensions with equal magnitudes. Let's use the new school methods making use of complex numbers to see if this is the case. Apparent power is the complex conjugate of the voltage times the current. Substituting in our given values, we arrive at an apparent power figure of 84 volt amperes at an angle of negative 45 degrees. You note apparent power magnitude is the same value we obtained earlier, only the angle has changed. As previously, we can resolve apparent power into real and reactive components. Real power equals apparent power magnitude times the cosine of the apparent power angle. Substituting in our given values yields a real power figure of approximately 59.4 watts. Reactive power equals the apparent power magnitude times the sine of the apparent power angle. Substituting in our given values yields a reactive power figure of negative 59.4 VARs. Note reactive power has a negative sign, indicating that the element in question is capacitive in nature because current leads voltage. Additionally, note, given the negative 45 degree angle, basically halfway between 0 and negative 90, real and reactive power have the same magnitude. Let's try one last illustrated example problem. Here's a plot of voltage and current where current appears to lead voltage by a full 90 degrees. The phasor representation of voltage would be 120 volts at an angle of 0 degrees, and the phasor representation of current would be 700 milliamperes at an angle of positive 90 degrees. Voltage and current are in almost every aspect exactly the same as in our previous example problems, only this time current leads voltage by a full 90 degrees. Our earlier thought experiment led us to believe that given a phase shift of a full 90 degrees between current and voltage, we should anticipate a zero-centered power waveform with equal and opposite periods of positive and negative power. Given all of apparent power is now being directed towards the cyclical interchange of reactive power, we should expect none of it to be directed towards real power. Long story short, for occasions in which current leads voltage by a full 90 degrees, real power is 0, and the absolute value of reactive power equals apparent power. Let's see if this is the case. Apparent power is the complex conjugate of the voltage times the current. Substituting in our given values, we obtain an apparent power figure of 84 volt amperes at an angle of negative 90 degrees. Again, you'll note apparent power magnitude is the exact same value we obtained earlier, since we're using voltage and current with the same effective values. Only the angle of apparent power is changed. As previously, we can resolve apparent power into real and reactive components. Real power equals apparent power times the cosine of the apparent power angle. Substituting our given values yields an apparent power figure of 0 watts. Given the power waveform is zero-centered, this is to be expected. Power consists wholly of a cyclical interchange of positive and negative power, and the average is 0. Reactive power equals apparent power magnitude times the sine of the apparent power angle. Substituting in our given values yields a reactive power figure of negative 84 VARs, meaning that all of apparent power is now being directed towards a cyclical interchange of reactive power. Additionally, note reactive power has a negative sign, indicative that the element in question is wholly capacitive in nature, since current is leading voltage by a full 90 degrees. In summary, all apparent power is being directed towards a reactive interchange because none of it is being directed towards real power, exactly as we anticipated. Let's summarize some of the observation about this series of illustrated example problems we just performed. Given voltage and current for every occasion was assumed to have the same effective magnitude and only differed by the degree of phase shift, note the apparent power magnitude, regardless of the degree of phase shift, remained the same at 84 volt amperes. That's largely the point of the old school methods. Take a voltage reading, take a current reading, multiply them together to get an apparent power magnitude. Too easy. In the single scenario in which voltage and current were perfectly in phase with one another, all of apparent power is being directed towards real power because none of it is being directed towards a reactive interchange. At the two opposite extremes, in which there is a full 90-degree phase shift between voltage and current, either leading or lagging, all of apparent power is being directed towards a reactive interchange because none of it is being directed towards real power. Note inductive occasions in which current lags voltage are defined as having positive reactive power, and capacitive occasions in which current leads voltage are defined as having negative reactive power. In between these extremes is where the magic happens. Note as current increasingly leads or lags voltage, less of apparent power is being directed towards real power, since more of it is being directed towards reactive interchange. Conversely, as current becomes more in phase with voltage, more of apparent power is being directed towards real power, since less of it is being directed towards the reactive interchange. While we perform these calculations for only a handful of scenarios, one could do so for other occasions to view the larger picture. In fact, if we were to plot apparent, real, and reactive power as a function of relative phase shift between current with respect to voltage, we should expect some very predictable behavior. You may wish to pause the lecture and stare at this graph until you appreciate it on every level that I do. Again, for all occasions, voltage and current effective magnitudes are the same, respectively 120 volts and 700 milliamperes, only the degree of relative phase shift differs. In this single scenario, in which voltage and current are perfectly in phase with one another, all of apparent power is being directed towards real power, since none of it is being directed towards a reactive interchange. If real and reactive power are to be considered different dimensions of apparent power, one can think of this single scenario as maximum real power and minimum reactive power. At the two opposite extremes, in which there is a full 90-degree phase shift between voltage and current, either leading or lagging, all of apparent power is being directed towards a reactive interchange, since none of it is being directed towards real power. Note inductive occasions in which current lags voltage are defined as having positive reactive power, and capacitive occasions in which current leads voltage are defined as negative reactive power. If real and reactive power are to be considered different dimensions of apparent power, one can think of these two occasions as minimum real power and maximum reactive power. Again, in between these extremes is where the magic happens. Note as current increasingly leads or lags voltage, less of apparent power is being directed towards real power, since more of it is being directed towards a reactive interchange. Conversely, as current becomes more in phase with voltage, more of apparent power is being directed towards real power, since less of it is being directed towards a reactive interchange. A special case scenario is being occasions in which there is a 45-degree phase shift between voltage and current, either leading or lagging, where real and reactive power magnitudes are equal to one another. Although we use some contrived values, the shape of this plot is generally indicative of the give and take relationship between apparent, real, and reactive power. I say again, as relative phase shift between current with respect to voltage increasingly leads or lags, less apparent power is being directed towards real power because an increasing amount is directed towards a reactive interchange. Alternatively, one can expect that as current and voltage become progressively more in phase with one another, more apparent power is directed towards real power because a decreasing amount is directed towards a reactive interchange. Think on this until we meet again. All right, that's about it for today. Ordinarily, I wrap lectures up with a series of example problems for the user. However, I'm going to publish another supplemental lecture entirely dedicated solely to AC power examples. Until then, this concludes this lecture. In conclusion, this lecture examined the different dimensions of AC power, apparent, real, and reactive, and we learned to calculate these quantities using a variety of methods. Remember to review these concepts as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.